This is video 5 for the Nuclei and Radioactivity unit. So in this one, let's start talking about environmental radioactivity. So we want to know, is all cancer caused by radioactivity in the environment? And the answer is no. If you live in a typical city, you are exposed to about zero point 0.2 rem of radiation every year. Most of this then comes from the radon gas seeping up from the rocks in the ground, and from cosmic radiation coming in from outer space. Some of this also comes from medical X-rays. So in 50 years, the typical American will be exposed to about 15 rems of mostly natural radiation. So let's calculate your chances of getting cancer from this. So if we do 15 divided by the cancer dose, which is 2,500, so that increases your likelihood of getting cancer from nature by about 0.4%. Remember, we expect 20 people to die, or we expect 20% of people to die from cancer. So that really raises it up to 20.4%. Not a huge increase. And since 20% of people die from cancer, we kind of wonder why. Some people think it's from pollution. Some think it might be something else, pollution, or maybe something else we can eliminate. So if we were just to remove that thing from our environment, we'll get rid of that 20%. However, if we add up all known carcinogens, we still can't account for the bulk of cancer. So another theory is that it comes from oxygen. Oxygen is a highly reactive element. So when we breathe in oxygen, it can actually break up our DNA. Now, we can't really say, stop breathing oxygen. So it's not like that's something that we can remove from our environment. But one of the prevailing theories for the 20% number is the fact that oxygen is reactive and we breathe in oxygen all the time. Now, the next thing I want to discuss is fission and fusion. So fission, I've mentioned that a little bit. Fission is a special kind of radioactivity. It's the sudden splitting. Fission kind of comes from the word fissure, like a split in the ground. So it's a sudden splitting of the nucleus into two or more larger parts, or smaller parts than the original atom. It was named in analogy to the fission of biological cells. Cells split. They go through fission as well. So we have two forms of fission, spontaneous and induced. Now, when it comes to spontaneous, the nuclei, or the nucleus, behaves like other radioactive nucleus. It sits around unchanged. And then, for about one half-life. And then, at some point that's completely random, it suddenly flies to pieces. And this is why, this randomness is why half-life is based off of probability. Half-life only works for a large collection of atoms. You cannot take a look at a single atom and then say, okay, after 5,730 years, this carbon-14 is going to split. It may or may not. It may split after 2 seconds. It may split after a million years. We don't know. It's impossible to apply the rules for half-life to single atoms. So if we take a look at a large collection of atoms, then we can say, okay, well, they, as a collective, they obey these rules for half-life. So this is spontaneous. It's completely random, and it may come from it may come from something that the electrical repulsive forces within the nucleus itself. There's several reasons for it. The next type is induced. This is man-made. So if we have the right kind of nucleus, if we hit it with a neutron, the neutron will be absorbed, causing the nucleus to become unstable and then breaking apart. And generally, once that nucleus has absorbed the neutron, it becomes a new isotope that has a very, very short half-life, and that's why it splits. Okay, so when a nucleus goes through fission, the bulk of the mass is usually divided up into the two unequal pieces that we call fission fragments. A lot of times also we call the original nucleus the parent, and we call the fission fragments the daughters. So these pieces, these daughter nuclei or these fission fragments, are usually radioactive with relatively short half-lives. And remember, if we have a short half-life, that means it's a very active element, and that makes it dangerous to humans. And these fission fragments are the primary source of residual radioactivity after nuclear weapons or a nuclear reactor has had an accident. Fusion, then. This is the source of energy for the sun. As a consequence, it's the ultimate source of energy for virtually all life on Earth. Basically, all energy that we have and consume comes from the sun in some fashion. So fusion refers to the coming together of particles, in contrast to fission, which is the separation of particles. So it may seem strange that you can get energy by bringing particles together, but it's true if you pick the particles correctly. The basic source of fusion in the sun comes from bringing together 4 hydrogen nuclei to make helium. And I've included the reaction, the nuclear reaction here, for how these hydrogens become helium. And basically, it takes about 4 hydrogens to make a helium. But there's also some beta radiation, some gamma radiation, and then this is a neutrino that's also produced as well. So this reaction does release, it's kind of like an exothermic reaction. It releases more energy than is needed for it to take place. All right, that concludes the unit on radioactivity and nuclei.